start the recording. Let's go ahead and go to, what is it? Videos, teaching. And in teaching, we're going to go to, in classroom, destruct. Study guide. What's this one? Okay, so this is the third link in there. Okay, so I'll go ahead and go over this one. So this is a bunch of multiple choice questions to begin with, so I think this is a good place to start. We'll see how far we get in our hour and 20 of doing this. Okay, yep. The advice here is good. Any notes, books, or other references at your disposal. Do not waste too much time leafing through materials. Okay. What they're saying, what I really like about their format is that they have these are worth, each of the multiple choice are worth 3 points, but you're allowed to put down a second choice answer as that's worth 1 point. If your first choice is wrong, but your second choice is correct. That's a nice thing. If I was doing a multiple choice exam, I'd do it like that. But you want to know something? I'm not that nice. I do short answer because those are easier to write. All right, so this one's a simple one. Suppose you've got A, B, C, D, and E pushed into that order onto an initially empty stack S. Then S is popped 4 times. Every time an item is popped off, it is inserted into an initially empty queue. If you then remove 2 items from the queue, what is the next item to be removed from the queue? In other words, after all these operations, what's the head of the queue? If you're trying to figure it out in your head, don't, because that's risky. Instead, we're just going to write it down and let's see. So we've got A, B, C, D, and E pushed into an initially empty stack, with this being let's see. Well, if we do A, B, C, D, and E, and let this be the top of the stack, right? And then we do, then we remove from the top E, D, C, B, and that's the front of Q. Now we remove the first 2 items. Now we remove the first 2 items in the queue. So we're left with B being the next. C being the next item in the queue. That's not too bad. All right. Pre-order traversal. So if the binary tree is in a pre-order traversal, what should the result be? Well, pre-order means we handle myself, then I handle my left child, then my right child. So we automatically know that A and B, dead wrong, because those start with 9. 9 is not a pre-order traversal. Or 9 would be the first thing in a post-order traversal. Okay. So 6, then I handle my left. 17. So C is wrong. So then let's take a look at this. 6, 17, 9 should be the next. Notice that basically D goes 6, 17, 22, 9, 4, 16, 12, which technically is breadth first search. That's not actually a pre-order traversal. So 6, 17, 9 is what we want. So by process of elimination, it's E. Now, I like this question a whole lot. A graph implementation that uses a 2-dimensional array to represent edges would be most reasonable for which of the following cases. Let's look at E first. None of these, since a graph can only be represented by a linked structure. Now, we know this is wrong because we've talked about how there's sparse versus dense graphs, right? You want to use a linked structure for sparse graphs and a 2D array when you've got a lot of edges. Okay? The reason being is that if you've got a lot of edges, if you've got a dense graph, having a matrix that basically can hold all possible possibilities of the edges isn't that space inefficient. On the other hand, it's space inefficient if you're using a linked structure and you've got a lot of edges. Suddenly you've got that nasty overhead of using linked lists and other stuff, right? Basically, if a linked structure, which we're talking about, typically the way I implement that is we use a hash table where the key is the node and the value is the list of all items in that node. So either a linked list or array list. You're going to be wasting memory either way in terms of overhead or wasted space, right? So eventually that overhead is going to be way too much, more than we want to know, especially since we're throwing it into a hash table, which is going to be wasting memory anyway. So, but we're not going to be wasting that much if it's a sparse graph. So sparse graph versus dense graph, we want to use a link structure for sparse and a matrix for a dense. So how do we decide whether something is sparse or dense? Well, that's an excellent question. Our textbook defines, I go with what our textbook says, which is we consider it dense once 25% of all possible edges exist. So in other words, right, if you've got 1,000 nodes, you've got approximately 1 million possible edges, right? 1,000 times 1,000, right? That's how many possible edges there are. And by the way, we didn't really talk about this much, but an edge from a node to itself is a perfectly valid edge, right? You can have that. So there are, so if you've got 1,000 nodes, you've got 1 million possible edges. So we would be looking for 1,000 nodes, we'd be looking for 25% of that, or 250,000 edges. So A, with 1,000 nodes and 1,200 edges, that is definitely not a dense graph. That is a sparse graph. There is relatively the same order of magnitude of nodes to edges. They're both O of n, right? There's an O of n relationship there, a linear relationship. Let's look at this, 100 to 4,000. So so with 100 nodes, 100 times 100 is what? 10,000 with 4,000 edges, that's a dense graph. Let's go and check the other ones. 1,000 nodes to 10,000 edges, that's 10,000 out of 1 million. That's a lot of zeros, but we can just cut them out. And I think that ends up being 1 out of every 100? Yeah, one. Yeah, that's 1/100th of the possible edges. And then 10 nodes with 20 edges, that's close to being dense. It's 20% of the possible edges that exist. The math on that one is pretty easy. So it's asking for most reasonable, this one, because 40% of all possible edges exist for this one. All right, suppose a binary tree is constructed of nodes that are instances of the following class, right? So here they don't use generics because, I don't know, they find generics to be hard for students or something. I don't know. They're hard when you start using them, and then you kind of acclimate, you know? It's like, oh yeah, I don't like it too much, but I understand it, kind of. Can at least get by with them, right? Public class node. So here, right, it's a binary tree of integers, okay? That's not really too important. It has a left node and a right node. What we concern ourselves with is this mystery method, right? Which returns a node and takes in a node root. It says, hey, if the thing to the right of the root is null, return myself. Otherwise, return mystery root.right. So you think about that, that's going to go all the way down to the right until it hits null. And then so it's going to return the rightmost node in the tree, right? That's what it's going to do. It's going to return the rightmost node of the tree, right? What's saying is that if there's nothing to the right of me, I return me. Otherwise, I'm going to do the same thing to the guy to my right, who's going to do the same thing to the guy to his right, and so on and so forth until we get to the bottom. It's sometimes hard to, it takes a bit of time to understand how to look at these methods, but that's essentially what that does. So we're going to consult 3 tech-savvy consultants and pay them exorbitant amounts of money, and we get the following 3 opinions about what the method does when we give it the root of a binary tree. Opinion, a consultant 1 says, it will return the last node visited by an in-order traversal. 2 says it will give us the last node visited by a post-order traversal. And 3 says it returns the last node visited by a level order traversal. And you have to look that up because Professor Rosen didn't go over level order traversals. But then you look it up and you find, oh, he just means breadth first search, right? If we're level order is breadth first. In other words, we go from the top, then to the root's children, then the grandchildren, and then the great-grandchildren from left to right. So which of these consultants are correct? And this is one of those annoying cases where we actually kind of go into math because it's the whole, proof by contradiction. So last node in an in-order tree. That one's actually pretty easy to prove to show that that one's correct, right? Because if I am the biggest node, if I'm the last order in last node in order traversal, that means I am the largest value. If I wasn't the largest value, I'd have somebody to the right of me. So, that's fairly straightforward. If I am the last guy, so that makes sense, right? If there was a node larger than me, it would be to the right of this guy. If the largest node is not going to be here, it's not going to be here, not going to be here, and it's not going to be located in this subtree over here. It's just not. So consultant 1 is correct. Consultant 2, last node visited by the post-order traversal. What the last node visited by a post-order traversal is always the root, right? Always do your left subtree, your right subtree. This is only going to be, 2 is only going to be true under the following condition. Basically, you've got the root, and then you've got a left subtree, and your right subtree is null. We don't need that much information. 2 is just wrong. It's not always going to, because we're asking which is correct regardless of what the tree is, right? As soon as but we can falsify 2. Falsification is what we look for, right? We can say, hey, your hypothesis is wrong because this contradicts your hypothesis. All right, breadth first search. This one's a bit trickier, so I'm going to draw. We're going to go with a perfect tree, which is what we don't want, but then we'll just start adding or removing or removing nodes to make it, to see what we're going to get. Okay, level order traversal says, I'm going to visit this guy first, then these guys, right? It's just breadth first search. Okay, it's not recursive, unlike the other ones, which is why we didn't go over it. It uses a queue. And once I say breadth first, you're like, oh, yeah, we don't need to go over it. It's breadth first search. Remember, so something to keep in mind, trees are graphs. They are just a special type of graph. Right? And they're specifically a special type of directed graph. Okay? So, level order traversal, for this case it works. And if we were to add another layer, it would work, or if we were to add another node over here, that would work. However, we can come up with a case where we would contradict, where 3 would be contradicted, which is if we remove this node over here, right? The rightmost node is this guy. This is the biggest node in the tree. But it won't be the last node visited by a level order traversal. This guy would be. So only consultant number 1 is correct. And really, maybe we should just hire him for our tree-related consulting. All right. So with a poorly chosen hash function, it is possible to have a situation in which the search time for n items goes to which? I mean, I can't come up with something that goes O of n factorial, because that's really difficult to write, actually, to do something that works that badly. But, I mean, this one's A, right? The idea here is that if you've got a poorly written hash function, right, then essentially what you got to do is that you got to look through everything in the hash table, okay, in order to get it to work. You got to look through every position, and there's n positions, so there you go. 1 is what we want, But it's not going to be worse than linear time, though, right? The worst case scenario, you look through everything. All right. We are not going to have this problem. We've already had this problem. This is where I got that first problem from our link from our first exam. So I'm just going to skip over it, which is dot next, previous, which one is which. This one is good. A police department wants to maintain a database of up to 1,800 license plate numbers of people who receive frequent tickets so that it can be determined very quickly whether or not a given license is in a database. Okay? Speed of response is very important. Efficient use of memory is also important, but not as important as getting your speed. So memory usage is important, but not as important as speed. Which of the data structures is most appropriate for this task, right? We want to basically say, here's a license plate number. Give me the person in the, let me see if it's in this person who's a frequent, frequent ticketed person. Given this license plate, is this person in the bad driver database? So we have 5 choices, 3 of which are hash tables with different amount of entries. Then we have sorted array and sorted linked list. So right out, sorted linked list is terrible for this situation. Why? Because to find something in a linked list, it takes O of n time. So literally the best we could do is just simply scan through the list. It will take O of n time to retrieve it. Because you can't, in order to find the middle, you'd actually have to iterate to the middle of the list. You don't have a pointer to the middle. You can't do binary search very well on a linked list. You can, however, do binary search on a sorted array very well, right? If we know it's going to contain up to 1,800 entries, we just put in 1,800 entries, make an array 1,800 wide of 1,800 entries. Very, very memory efficient. If we were going for memory efficiency, this would be the best option. 1,800 entries, sorted array, binary search takes log n time. Takes a maximum of log base 2 of 1,800, which is more than 8, because log base 2 of 256 is 8. So now let's look at hash table with open addressing using 1,800 entries. That is not a good hash table. That's actually approaching, that's a full hash table, right? If we've got a full hash table, that's like looking, if you're trying to find, if basically you've got a full hash table and you're trying to find something like that, it's like trying to find a parking space for your car in a full parking garage, right? You know where you want to go. It's pretty close, but you've got to find that single open parking space in the parking garage. Think about how long that takes. It takes forever, right? You're not even sure if it exists. And then it turns out that basically the SUV next to you parked very badly, and you can't park there anyway, and now you've just wasted $10 going into the parking. I'm not bitter. I'm not. All right, but fake story, but anyway, it's still funny. On the other hand, a hash table with open addressing using 3,600 entries, right? That's going to be, that's basically a parking garage with half the spaces open. Very easy to find a space. Sure, you might go, ooh, is that a spot there, right between these two cars? And you realize somebody just parked their moped in there, and you might have to go past slightly, right? But it doesn't take that long because only half the spaces are taken, right? Oh, so the space you were looking at turned out to not be a space? Well, there's one right next to it, right? And we bear this out with the equation we saw. Basically that if it's half full, it takes basically 1.5 probes on average to find your spot. In other words, if you're looking in this database, it's going to take, on average, 1.5 checks versus the more than 8. I don't know what log base 2 of 1,800 is, but it's more than 8. This would take log base 2. Now, we're approaching diminishing returns over here, right? It'll look slightly faster, but again, efficient use of memory is also important, but not as important as speed. But when you're talking about, am I averaging 1.5 versus like 1 or 1.2, it's not that important. So D is, I would make the argument, is the best. But if you wanted to balance your space and memory efficiency, then I'd go with B. So D is the correct answer for this one. All right, Huffman tree. So again, the Huffman tree, so the question I gave you on your practice exam and on your exam, okay, those are going to be, that kind of question is going to be on the final exam, okay, not this kind of question. Just remember to review Huffman trees. If you need some practice, there are online Huffman tree generators, so you can basically create your own text sequence, right, or your own frequency table, and then see what tree generates from that, okay? So you can check yourself. So Huffman tree is constructed for text document containing 5 characters. I'm assuming it means 5 different types of characters versus just only 5 characters, right? 5 different types of characters. The character E is the most frequent character, followed by I being the next most frequent character. So which is the most likely, which could be a Huffman tree for this document? 1, 2, or 3, and then we were given options like 1 only, 2 only, 3 only, 2 or 3, or none of them. So 1 is completely incorrect because with Huffman trees, which fortunately everybody remembered, for this exam, like occasionally I have one or two students who forget this, but here, great, everybody remembered. Only leaf nodes can have characters in them. The internal nodes are just kind of empty. Right, so 1 doesn't work because I and T are internal nodes. Okay. Here, E is the most frequent character, and the next most frequent character is I. That's plausible, right? We could have like 1 million frequency over here, and then maybe 1, 1, 1, 2. Right? So 1, 1, and 1, 2. Well, let's see. Well, we can come up with something. Let's see. 1, 2, and then, 1 and 2, and then 1 and 1, and then 4 and 5. Yeah, that would work. 1 and 2. Actually, no. 1 and 2. But the point being is that these can balance out. We could even have this be like 1, 1, 1. It's just, I think it will work. But we know that 3 is wrong also. Now, why is 3 wrong? Because I and E are supposed to be the most frequent characters, but they're here at the bottom with the most bits, right? Takes 1, 2, 3 bits to encode an E, and 1, 2, 3 bits to code an I, but your most frequent characters should have the least number of bits. So E, possible. And I know there's a configuration you can get for this. 2, 2, let's see. 2 and 2 here would make 4 here. So, 2 and 2 and 3 and 3 would do it. 2 and 2 and 3 and 4 specifically would to get you this configuration. So that would work. So 2 only. All right. So an array of 7 integers is being sorted by the heap sort algorithm. So for heap sort, remember, what we do is we construct a max heap, right? And then we we heapify it into a max heap in O of n time, and then we proceed to sort it, taking n log n time. So after the initial phase of the algorithm, where we turn it into a heap, but haven't sorted it yet, which of the following is a possible ordering for the array? A, B, C, D, or E? So we know D is wrong because I just said we need a max heap. So really what this is asking is, which of these arrays represents a max heap, right? So 85, and that just means that basically that, so 85, so we could draw this out. 85 and 78, 45, and then the children, so this is the root, these are the children of the root, and these are the grandchildren, right, for the heap. And what we need is that we need the heap to be, the root of each heap and subheap needs to be the biggest thing in its heap or subheap. So 85 is the biggest thing, that works. So 78, what is 78's children? 78's children, if you remember the formula, are, or you can just visualize it, you've got 51 and 53. So that works out. But 45 is smaller than its children, so A is wrong. 85, 49, 78. 49, bigger than its children. 78, bigger than its children. That seems to work. 78, bigger than its children. 49, smaller than its children. C is wrong. Now 85 is bigger than its children. 51 is smaller than one of its children, so that's wrong. So the only possible answer was B. Right? Remember, and you can draw it out with 85 at the root, then you've got these two children, and then these four as the grandchildren. Right? There's a formula we had where basically I think it was just you multiply the index and add 1 and then add 2. Okay. So we constructed this binary tree by inserting a bunch of items into an initially empty tree. I think this is a really good question, and I'm probably going to steal this for exam 2 next year, where here's a tree. Tell me which of these would not produce this tree, right? We've got a bunch of items added to this tree. Which of these would not produce the tree? So obviously 5 comes in first, right? Got to be the root. So let's look through this. 5, then 3, then 4. That works because 5 followed by a 3 followed by a 4. Then 9, then 12, then 7, then 8, then 6, then 20. Now this all works because what would make this wrong is that basically if I got something like 5, 4, 3, that would not result in the tree. We're asking which of these sequences inputted in this order would it end up with this tree. We're looking for the one that does not follow that. 5, 9, 3, so no gaps. 7, 6, 8, 4, 12, 20. That works as well. 3, 4 is over here. That's fine. 9, 7, 8, 6, 12, and 20. Now what about D? 5, 9, 7, 3, and then 4. 5, 9, 7, 8, 12, 6, and 20. That also seems to work. 5, 9, 3, 5, 9, 3, 6, 7. So that wouldn't result in this tree because we have a 6 before 7, but we've got a 6 being a child of 7 in our tree. That doesn't work out. Okay. I'm going to skip this one since it's fairly easy. We just did this on the exam, but it's not going to be on exam 2. It's going to end up being a very jagged tree, though, which is why he uses it as an example. It's like, interestingly enough, it's a jagged tree. It's great for answering part 2, which is this. So this part is going to be on the exam, something like this. This is one of the questions we asked about hash tables. So this will be on the exam, specifically part A. Part B, not so much. Part A will be. Okay. We're given an initially empty hash table of size 7 that uses open addressing. The following is a sequence of keys that needs to be inserted. Insert these keys using each of the following approaches. If an overflow occurs, say so and indicate the element that causes the overflow. Every exam does it differently. Sometimes we say, hey, show me which the element that gives me the overflow. Sometimes just count how many check probes each item had to go through before it landed in its spot, right? That kind of thing. I'm just going to draw it. Give me a second to pull up the screen up here and redirect it. So we've got, okay. So we're going to insert these elements, which are, going to write them on the board so you can see them later. But we've got, I'll write them over here and then draw the next one. We've got 15, 17, 8, 23, 3, and 5. Now, each of these guys has we're going to be using the hash function. So these are all the keys. Forget about the values. We don't care about the values for this problem. We just care about keys. So we want to find out where the key value pair for this key is going to want to go, or going to end up, if we insert them in this order. And the hash function we're using is x mod 7. So the key modded by 7. So what I like to do first is figure out where do these all go, right? What index do these all want to be at now? they could be there, where would they be? So in other words, let's just do all these numbers mod 7. So what is 15 mod 7? That's going to be 1. Because now, for basic math like this, easiest thing to do for this is just keep subtracting until you can't subtract, until you would end up with a negative number. Stop before then and see what the remainder is, right? So, right, 15 minus 7 gives you 1, right? 17 minus 7 gives you 3. 8 minus 7 gives you 1. 21, right? You know that's a multiple of 3. You know that 21 is a multiple of 3. So 21, 22, 23. So 2. Right? 3, and then remember, this is one that I see every so often. If you have a number mod 7, right? So if you have a smaller number mod bigger number, your answer is the smaller number, right? X mod y equals x, x less than y, right? That is the rule. When x is less than y, x mod y is equal to x. Or more simply put, when you try to divide a smaller number by a bigger number, you can't. You can't divide it evenly. All that you're left with is the remainder. So this is where all the items want to go. So I'm going to go ahead and, because it's easier for me to do it horizontally, I'm just going to do it horizontally instead of vertically. And also because we do it horizontally on our exam. So index 0, 1, 2, 3, 4, 5, 6. Okay? So we're going to see, so first thing we insert is 15. 15 is going to go into index 1, right? 17 is going to go into index 3. 8 is going to go into index 1, but it can't. Why? Because it's already taken. Now, there's many ways to resolve collisions, right? This is what we call collision. There's many ways to resolve collisions. How do we resolve this collision? Linear probing, which means look for the next available spot, next being defined as the literal next spot to the right. So I'll just draw this to indicate. 23 will be trying to go to 2. It can't. Then it's going to try to go into 3. It can't. So it goes into 4. Right? And I'm just simply drawing the paths for each item. Right? Maybe not the most intuitive way for it to do, but it works for me. 3 tries to go into, and the reason I like this is because you can count how many things collide with that space as well as the amount of probes each guy needed, right? This needed 2 probes, right? 1 probe, 2 probe, find an empty spot. This guy needed 3 probes. You see that there's 2 collisions here. Now 23 at index 2, we did that already, so 3 at index 3. Can't go into here, can't go into here, so 3 goes into index 5, and 5 can't go into index 5, so we put 5 into index 6. Right? Now for these problems, we do not assume that you rehash, right? We don't assume that you have to basically you don't have to rehash the you don't have to grow your array, you don't have to make it bigger, right? You just assume that the hash table won't grow in size. Okay, second problem using quad. We're going to just go over this simply the second problem so we can get some more practice on this. This is using quadratic probing. So it's the same numbers, right? Same numbers. Same numbers, but we're going to resolve it using quadratic probing instead, right? Really what we care about is linear probing, but I figure same problem gets us more used to this problem. Okay, so 15 mod 7 goes into here. Our first initial steps are the same, right? 15 goes into here, 17 goes into here, right? Our only difference is when we get this, right? So 8 goes into 1. 8 can't go here, so it's going to go into 2. Index 2. Because with quadratic probing, what I'm going to look at is, I'm going to look 1 squared away first, which is 1, then 2 squared away, then 3 squared away, then 4 squared away. Okay? So now, so we've done this one, this one, this one. 23 needs to go into here. Can't, so we're going to look over here. Can't. So we need to look, instead of going 1 away from the original space, that's the key, from the original space. We're going to, sorry, and then instead of looking 2 away from the original space, then 3 away, we're going to look 1 away, then 4 away, which 2 squared. 1, 2, 3, 4. So we're going to put 23 over here. And incidentally, 3 only has 1 collision to deal with. And then we can drop 5 right over here. The next 5. So we did not go over double hashing, which just simply says, hey, we've got a secondary hash function to use if the first one doesn't work. But that's okay.
Is it possible that both will work?
I suppose, but I'm not really sure how we deal with that, because I didn't really ever learn that, embarrassingly. So, but I mean, all right. So here we've got a graph. I actually think this is a terrible graph, but we're going to do it anyway. Oh, and let me set this up so that we get our screen back. All right. Perform a depth-first traversal of the algorithm of the graph shown above, starting with vertex C. So now the way we deal with this so that our answer, so everybody comes up with the same answer, is that we typically say if there's a tie, we give you a way to break the tie. And generally there's 2 ways to do it, or there's about 3 ways to do it, which is like, oh, if there's a tie between nodes you want to visit either them alphabetically first, or select the one with the smallest weight, select the edge with the smallest weight, or select the edge with the biggest weight, right? The rules are fairly simple for breaking ties, and we specify what they are, right? There should never be any ambiguity. So here, we're going to perform a depth-first traversal of the graph shown above, starting from this vertex over here. We are going to select the smallest edge first. In the space below, which lists the vertices in which they are visited. Okay. So this is going to be, I'm going to go ahead and just simply boot up Guinea, or rather we already have Guinea, because we don't really need to check off. We've got visited, and we've got our stack over here for depth-first search, right? What we've already seen and what's on our stack. So we're going to visit C first because we're starting with C. The problem specified that we're starting with C. See? Starting with C. And so we say we visit C, put it onto the stack, and we're going to go and visit one of its neighbors. Its neighbors are B, E, and F. Right? We want to visit an unvisited neighbor of C. B, E, and F. We select the one that has the lowest, that has the smallest edge. So we're going to go ahead and say B and put it onto the stack. Okay? So now we're at B. Check this top of the stack to figure out where you are. Okay, B. So I've got a bunch of neighbors. I've got C, E, F, E. In fact, all the other nodes are my neighbors. Now, 5 does happen to be the smallest edge, but I've already seen him. So I'm not going to go and visit him. So the other edges are 13, 17, 20, and 18. Smallest edge over there is to A. A. We're now at A. A has edges to B and D, but we're going to select the smallest edge we haven't visited, which is this one, which is the edge to D. Okay, and D, we visited D, but now we're at a dead end, right? Because we visited A and B already. So what we do is that we pop off the stack to get to backtrack. Now we're at A. We're at a dead end again, right? We've already visited D and B, right? Pop off the stack. We're at B again. B is not a dead end. We visited A, D, and C already, but we haven't seen E or F. So what are my choices? E at 20 and F at 18, right? Costs, F is the smallest one, so I'm going to go to F. Put that onto the stack. F is a dead end, right? Already visited B and C. So I'm going to pop off the stack, go back to B. B has only one edge left, which is E. Okay. Go to E. E's a dead end. We've already visited C and B. So pop off the stack. B's a dead end. We've already visited all of its neighbors. C's a dead end. Pop off the stack. Stack is empty. We are done. That is breadth research. You don't have to record, by the way. I'm going to be uploading this. So I'm recording this now. You're more than welcome to. All right. Breadth first search is a bit easier, right? Select the smallest edge when appropriate. Breadth first search starting from C. Okay. Again, we're going to have a visited and a queue this time. But what goes into the queue is a bit different, right? So we visited C, all right? Or rather, we've seen. So here what I'm going to have is a seen, a queue, and a visited. Because you visited nodes as you see them in depth first search, essentially. Okay. Visited is our output. So first we're going to start with C. We've seen C. We put it into our queue. So now we start by dequeuing from our queue and asking, hey, who are the neighbors of C? They are B, E, and F. Now we want to visit them in order of the cheapest edge. So we're going to visit B first. B, F, we've seen. Then we'll visit, let's see, C is 30, E is 22. So we're going to visit B and E and F. And we visited C. We just finished visiting C because we've identified all of its neighbors and said we want to visit them. So next in our queue of traveling is to go to B. So we're at B now, so I'm going to move it to business visited. So who are B's neighbors? B's neighbors are C, but he's already in our queue and been seen. F, E. Seen might be better. A better word for seen might be identified, but seen is shorter. That's why I'm using seen. So I can see it. I want to go there. C, F, E, already on there, but A and D are not. So A and D. So B to A is that. B to A is 18, followed by 17 to D. So EFAD. And then we're done. And then we would visit E, and then F, and then D, and then, then A, then D. So that would be our answer. And the reason being is because, right, once we've identified all the nodes, we just simply would visit them in the order they appear in the queue. Right? So C, then we visited B, F, which are its first neighbors, and then AD. So really what the whole order that we visit things in with selecting the smallest edge first is determining which of my one-step neighbors am I going to visit first, then which of my two-step neighbors am I going to visit first. So now, Dijkstra's from D to E. We want to find the shortest path from D to E. List in the order they become known, all vertices with the shortest path determined in the order of solving the problem, blah, 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 blah. Okay, we want to do Dijkstra's, so we're going to do Dijkstra's on all the nodes because that's going to give us D to E. So we have, so again, if you set this up like Dijkstra had originally, you have S and you have V dash S, and then you have P's. Sorry, then you have D's and P's, which is terrible. Instead, you have really what you want to have is done, to do, right? All the nodes you have that are done, all the nodes that are left to do. And then, actually, it's better to, I think this is one of those cases where I want to use an Excel spreadsheet just simply because, let's see, what is it called? Calc. LibreOffice Calc. So we're just going to make a chart over here, a graph of sorts. Let's go ahead and up this to like something that's reasonable to see. Right? And I'm just simply going to track over here. So DE is typically the distance to a node. Prev is how we got there. Let's go ahead, and 40 is a bit too big. Distance, previous node, and then S and VS you really don't need, because really what you need is just simply saying, am I done with this node? So done. And that will basically I'll put an X here if it's done. So let's list the nodes in order. A, B, C, D, E, F. We're starting with C, so C is automatically done, right? And that means its distance is 0 and it has no previous node. Okay? So for the other nodes, we need, wait, are we starting from C or D? I think it says from D to E. We're not starting from C this time. So that's easy enough to change. Boom, we're starting from D. So now we have to, and basically everybody else starts out with a distance of infinity. We initialize it that everybody has a distance of infinity. And that their previous, and so we can get from D to any other node at infinite cost. And its previous, in the previous, so basically this chart says, how do we get to E? You get there from D, and it takes infinite amount of cost to get there, because there's no edge. And so now what we do is we now initialize this Dijkstra's algorithm by saying, hey, which of these guys, let's figure out these actual distances for the edges D has. So D has an edge 2, right? What we technically do is say, hey, okay, D has the lowest distance. We find the node with the lowest distance. D has the lowest distance. Or rather, we find the node with the lowest distance who is not done. Is D done? No. Find the node with the lowest distance, and then let's go ahead and see if we can update our distances. So D to A is D to A is 10. Is 10 less than infinity? Certainly hope so. So we update and say we can get from D to A with by a distance of 10, and then we can get from D to B with the distance of 17, with a cost of 17. Okay, those are all the nodes, so now we're done. Next, we choose the node with the cheapest cost, okay, who is not done. That would be A. Okay, so let's see. A to B is 13, so we can get to B from A with a total cost of 13. Is that cheaper than the current cost we have? No, that's 23 is not less than 17. So that's the only additional information A has to offer, so we're done with that. Now let's look at B. Okay, because B is 17 and then the rest are infinite. So 17. Okay, B to C we can get from B to C for a cost of 5 plus the cost it was to get to B. Right? We're looking at the path, at the cost of the path from D to other nodes. So, what we're doing is saying B to C plus the cost it got to get to B. 22 is less than infinity. Yes, it is. So we can say 22 B. What about B to F? B to F is 17 plus 18, 35. And what about B to E? That is 37, which is less than infinity. Okay. Next, let's look at these. C. C is the next shortest one. C's edges are 22 and 30. 22 plus 22 is 44. That's not cheaper than 37. And 22 plus 32 plus 30 is 52. Which is not cheaper than F, so we don't have to do that. Next, we look at the next one. F. F provides no new routes, and E provides no new routes. So those are the cheapest costs to get from D to any other node. I highly advise you trying Dijkstra's algorithm on your own graphs or on practicing that problem. Okay. Same graph, but these are for Prim's algorithms and other stuff we didn't go over. Okay. Let's see. Coding problems now. Okay. Complete all the following problems. A node has a key and a data and a left-right. Okay, here's the search algorithm. Write it so that it uses iteration instead of recursion. I'm not going to bother doing that one because with trees we want to use while loops, or with trees you want to use recursion. But for here, the way you would solve this one if you want to try it, because I want to get to other coding problems, okay, is you would basically create a while loop, like while we're not found and while it's not null. Check the value. If it's left, basically you'd have a loop saying, hey, while the current is not null and it's not the value I'm looking for, right? And then if it's left, go set current to be less. If it's less, go set current to be left. Otherwise, go to the right. It's not too hard. This one's more interesting. Write a Java method named mirror that takes a reference to the root node of a binary tree and creates a new tree with its own node that is the mirror image of the original tree. So, for example, if we gave it this root, this guy, then it would create this tree. Where 1, 2, and so here what we're seeing is that the is basically we've got a lot of stuff that has been switched. Really, I've got, okay. So save. Home. Okay, I'm just going to code this up as a method with syntax highlighting. Public static node mirror node root. Okay. So basically what we want, so first thing we want to do is that, right, we're going to be basically returning a copy of everything this time around. So anytime we are making anything, it's going to be a new node. So here, first off, we want to figure out what are we going to do if root is null, as always. If root equals null, then I'm done. Return myself, or sorry, return null, because there's nothing there, right? Otherwise, if I'm not null, that means I got to actually figure out what I'm going to do. So let's go with node mirror root equal to new node. Actually, I'll go ahead and move this over here so that we have room to see. Then let's see now. There we go. So we know that basically, regardless, one item, I'm not going to, myself, I'm not going to worry about how I'm mirrored. So mirror root is equal to new node, and that is going to have root dot item or root dot data, I don't really care which term you use, as the item in it, right? We're going to copy that item. And at the end of all this, I'm going to return, I'm obviously just going to have to return the mirror root instead of returning root. Okay, so let's go ahead and see. So suppose I pass in 1, what's going to happen? I'm going to basically swap 2 and 3, right? But that's not all. 2 is going to swap its own children, and its own children are going to swap its own children. So this is going to need some recursion. So node mirror left and node mirror right. And then at the end of this, we'll say, hey, okay, so the mirror left is going to be equal to it's not just that we want it to, we could say is equal to new, we could do like new node root dot right, because my left is going to be the old right. My left is going to be the mirror, so it's going to be the right side. Or root dot right dot item, but we don't know that it's going to be an item. In fact, what's best to do is say mirror left is equal to mirror my left, and let's remember, my left node doesn't actually have to be isn't just one node. It's going to be the root of an entire tree or subtree, which is going to be mirrored. So mirror root dot right. Mirror root dot left. And then mirror root dot left is equal to mirror left. Attach the nodes. In fact, we can shorten this even more by saying, hey, my left side is equal to my mirroring what happens when you mirror my right. Now we know that recursive algorithms are short. This looks very short, so let's go ahead and just kind of work our way through it. Right? So if I'm 1 and I've got my children 2 and 3, I'm going to basically say, hey, child, let's go with figuring out what this side is going to do, 3. Right? I'm going to go ahead, if I'm the root, I'm going to create a clone of myself, and I'm going to say, hey, my left side is equal to the mirror of my right side. I'm going to call that on my right side. That will return a new node. And because it itself is going to mirror its left side and right side, which are going to be null, so that's great. So null, null, that's right. And so then I'm going to attach it to my left side. My right side will be the mirror of the left side. So boom, the 2, which will call it on its children 4 and 5. And it will, by calling that on its children, it will proceed to recur. So this is actually all it needs. Set my left equal to the mirror of right, and my right to the mirror of left. And then I return myself to whoever called me. What is the running time of this? Well, O of n, because it hits every node exactly once. Well, or rather, every node, basically you call mirror on every single node once. All right, so it is 1:30. Let's take a look at one of the other exams really quickly. Let's see this one over here. All right, I just want to check really quickly which are the questions on this one. Dijkstra's topological sort. BFS, yeah. Scenarios. Let's go with another. This one over here. Specifically, I want to go over this problem because I didn't go over a sorting problem. So let's look at merge sort versus insertion sort. Okay. For each algorithm, what is the worst case asymptotic upper bound? In other words, what is the big O of the running time if you know, additionally, for each of these algorithms that your input is already sorted, your input is reversely sorted, and the list containing n copies of the same number. For each case in sorting algorithm, state your answer and justify it in one sentence. Okay, so let's go insertion sort, and then we're going to consider merge sort. Although merge sort is super simple because the answer for merge sort is if we know that it's sorted, it's n log n. If it's already reversely sorted, it's n log n. If it is n copies of the same number, it will also be n log n because it always runs n log n because of the way divide and conquer just will work. It will split it, split it, split it. It will have log n layers, and then each layer will take O of n time to merge. Doesn't matter what it is or how much time is in it. So if you want consistency, merge sort's the way to go. So let's just consider insertion sort then. What if your input's already sorted? That is the ideal best case for insertion sort. It will take O of n time for it to discover it's sorted. Because what you do is you say, oh, this item is, you'd go, let's see. So you'd have 1, 2, 3, 4, 5, 6, you'd have these numbers, right? And you'd go, oh, 1's already there. I don't need to push it down. Let's go ahead and push 2 to its proper spot. Let's push it down to its top proper spot. We're already there. Move on to the next item. 3's already pushed down to its proper spot. 4, 5, 6, and 7, right? Basically, you check and you see you don't have to move any of the items. On the other hand, so everything's already in its proper spot. Don't need to put, nothing will ever get pushed down. 3, 2, 1. On the other hand, if it's reversely sorted, this is the worst possible case. It is O of n squared because we say 7 sorted. Let's insert 6 into this sorted position. 6 needs to be pushed down. Okay, now let's push down 5. 5 swaps with 7 so that we can push it down, and then 5 swaps with 6 so that we can push it down. Then 4 swaps with 7, then 6 and 5, and then 3 swaps with 7, 6, 5, 4, then and so on and so forth. So the total number of swaps is is equal to 1 plus 2 plus 3 all the way up to n minus 1 swaps, which we know is O of n squared. Okay? And then turns out that a list of n copies of the same number, in other words, like a bunch of 5s or something, also will take O of n time, because as far as insertion sort's concerned, that's already sorted. Right? It's not going to try to swap them because insertion sort is what we call a stable algorithm, which means if you care that your first 5 in your input is the first 5 in your output, then the insertion sort will keep it that way. It's a very weird edge case. Let's see. Suppose you have a set of numbers where you over some time period do a constant number of insertions and a linear number of lookups of the maximum. So in other words, we are going to insert like 100 times, let's say, and then we have some O of n number of lookups where we check the biggest item. To maintain your set of numbers, you can choose either between a heap or a binary search tree. If you're interested, assume you're interested in minimizing the average total runtime over a time period. For each structure, what is the asymptotic upper bound on the average case runtime, and which of the structures should you choose? So, if we have 100 insertions, basically, and inserting an item takes O of n time, and then finding the biggest item in there, assuming we've got this balanced, will take log n time, right? But we know that we've got a constant number of insertions, so we don't really need to think about that too much. So let's compare it to the heap. Heap, on the other hand, each insertion takes log n as well, right? It's the same amount. To insert into a heap, log n time, versus adding to a tree takes log n time. But to find the biggest item in the heap at any point takes constant time to find the biggest item in the heap if we keep it as a max heap. So, yeah, I would totally want to go with the heap there. Suppose you are actually interested in the worst case. For each structure, what is the asymptotic upper bound? Oh, right, because it's average case and worst case. Worst case scenario for a binary search tree is that it's not balanced, right? So insertion would be terrible, and finding the item would take both of those would still be O of n, and finding the largest item in a heap, assuming it's a max heap, still constant. I don't really think I understand that question too well if it's the same, because honestly it's again the same. But here they're talking about the average case, and we really didn't go into average case too much. On average versus the worst case scenario. On average for trees, everything is log n time. But for heap, the heaps are set up so that it's always going to work the same way. Okay. So, here we go. Suppose we have a hash table and we've inserted some elements. When you inspect it, you see that the result of it looks like the picture below. Being a good student, this realizes this is a problem. So first off, this is a hash table. There's 19 possible entries in it, right? 19 slots, 20 possible slots, indices 0 to 19. And we note that this is resolving collisions using chaining, because each of these indices is a linked list. So what is the problem here with this hash table? Anyone? Yes? It's got a bad hashing function, possibly. But more specifically, it's not evenly distributed. But it's probably because of a bad hash function, because part 2 says, give an example of a hash function that could give rise to this behavior. How could we get this? How did we possibly get this? So, let's take a look. So, index 0 holds 0 and 30. Index 2 holds 21, 31, and 1. Index 4 holds 2. Index 6 holds 33 and 63. 10 holds 15. 12 holds 26 and 6. 16 holds 38 and 8. What's common between each index? Yep.
The index of is the last digit.
Yep. The index, you leaped all the way to the end there,
yeah.
Right? The index is, if we look at this, we notice that basically 0 has zeros. These all end with 1s. These all end with 3s. Which means that somebody modded by 10 at some point. And then notice that we're only at even indices. So what happened is that the hash function that could lead to this behavior is basically x mod by 10 times 2, where basically we modded by 10 and then multiply by 2. So in other words, rather than modding by the length of the hash table, which it would be a better hash function, slotting by the length of the hash table. Probably, because honestly, it's not an even number, right? This isn't even. A better hash function, if we wanted to guarantee it, would be modding by 19 and just let that empty slot in the back just kind of sit around. But honestly, that's and that's okay because we're resolving this with chaining as opposed to ordering. But yeah, that's a bad hash function. All right. So let's see. So that is 140. I think I'm good for the review right now. So for the last 10 minutes, if you want to just briefly come and get something demoed, I have to be out by 1:50, so not much time for demoing. So let me go ahead and talk about demoing for the last bit. I plan on coming in for office hours during the study day of Wednesday, so I plan on coming in next Wednesday. If you need to demo your stuff, remember you've got tomorrow. You need to turn in your stuff by Monday. And then you just have to get it demoed by the final exam, which means come to office hours or arrange to meet or email Sheng to demo your remaining stuff, right? Also, please note that your student feedback forms are open. Please, please, please fill those out. And if you liked me, give me high ratings. And if you didn't like me, don't fill it out, please. No, I'm kidding. But in all seriousness, just those are really used and looked at, you know, when it comes to like evaluating for promotion as well as for basically any awards, so for teaching. So those actually do impact, you know, professors. All right, but we do, and I do look at them at the end of every semester, and I do try to make adjustments based on that. All right.
Yeah, Professor Rosen, our final's on Wednesday, correct?
Tuesday.
Tuesday?
Yeah.
What time?